Okay, let's go ahead and get started. Thank you for coming to this week's colloquium. Today we're honored to have Jinyang Liang from the Institut de la Recherche Scientifique in Montreal. Um, and he's a graduate of University of Texas and then was a postdoc at Washington University and Caltech, where he was in the group that did all kinds of powerful things with very, very high-speed cameras. And he's won numerous awards and is a chaired associate professor at the Institute. So, Jinyang, if you're ready, go ahead.
Great. Okay. Thank you, David, for this nice introduction. So I'm Jinyang, and let me start by thanking David Florian for inviting me to visit the Wyant College of Optical Sciences. I've had a rather intense but very fruitful discussion with some of colleagues today. So in this talk, I'll be talking about coded optical streaking for real-time ultra high-speed imaging. So I look forward to, I guess, more discussions in this colloquium. So before I get into, oops, just 1 second. So the projector doesn't really like my computer. So if there's a crash, I apologize. Okay. But let's see. Good. Okay. Before I get into the topic, I would like to use I guess a few minutes to introduce my university, my institute. So I'm from the National Institute of Scientific Research. In French, it's Institut National de la Recherche Scientifique, and we're part of the University of Quebec system. So Quebec is in the I guess northeast corner of North American continent. So I mean the Atlantic is here. I think Boston is somewhere here. So because yeah, we're in the north, you guys are in the south. So I mean the landscape is totally different, right? So I took this image yesterday, showing beautiful UA campus, right? So I mean green glass, blue sky, 25 degrees Celsius. But I mean, if you look at what my institute looks like, it looks like this, right? So currently, I think we're covered by 20 centimeter snows, but it can get lots of fun, right? Especially in the winter. So IRS is a small size graduate-only university. So a part of University of Quebec system. So we have a bunch of research centers scattered around in the province of Quebec. So my lab, which is located at the suburb of Montreal, is called the Laboratory of Applied Computational Imaging. So where we use ultrafast photonics and computational techniques to design and develop novel computational imaging systems, and we use it for various of applications, ranging from material science to manufacturing, also in biomedicine. So Wyant College of Optical Sciences has been a great impact of my career, right, in all sort of stages. So, I mean, for example, if I would like to list some textbooks I used either when I learned the class or the class I'm teaching. I mean, there are a great deal of them. And also in daily research life, I'm inspired by some of the great works generated by the colleagues here. So, for example, I was inspired by Professor Takashima's work in the DMD-based LiDAR, where we developed a DMD-based ultra-high-speed imaging system, which I will show in, I guess, in 5 minutes. And also, I've been followed quite closely to the career path of David. So his work in the CAC-C, CAC-T, and also gigapixel camera literally made my research possible, right? So it's kind of like a dream come true for me to visit one of the holy cities, right? I mean, for all people who is doing optics, right? So um, inspired by David's work, one of the I guess standout work since my postdoc is compressed ultrafast photography CUP, right? So it's one of the fastest cameras all over the world, and we have been using it to document many fundamental light phenomena. So, for example, this is a light refraction, right, at the air-resin interface. We imaged at 100 billion frames per second, and we can see a picosecond loss pulse gets spatial focused at 2.5 trillion frames per second, or we image the time of arrival of 2 femtosecond laser pulse at 5 billion frames per second at UV. And we can also use CUP for different applications. For example, we documented the polarization dynamics of early stage plasma emission. And we can see some relatively bizarre but very interesting instantaneous light scattering pattern. And this one formed a photonic Marcon, or we can use it for spectrally resolved fluorescence lifetime microscopy. So in my lab, we're also doing high-speed 3D imaging. So we use a band-limited imaging system to project a single binary DMD pattern, digital micromirror device pattern, to a grayscale sinusoidal pattern. So we can do a real-time single-point depth tracking at 1 kilohertz. At the same time, we use the system for various applications ranging from fluid dynamics to inspection and full human body imaging. Yeah, as you can probably see, my lab is focused on high-speed imaging. So besides that, we're also working on high-speed light field imaging and tomographic imaging. So this work of Jinyang, so we designed a high-speed coded-aperture light field imaging to study the behavior of disease model zebrafish. And Yiming and Samik, they also developed a compressed ultra-fast tomographic imaging and use it with a dynamic transmission electron microscope in my university. So, but today I would like to focus on a rather specific topic of streak imaging. So there will be 4 parts in my presentation. I'll first talk about optoelectronic streak imaging, how does it work and what is the limitations. And then I'll talk about how, if we use all optical method, we can overcome these limitations. So what are the advantages? What are the strategic of implementation? The third part of my talk will be focused on 3 recent development three recent developed image modalities in my lab that embodies the concept of coded optical streak imaging. And finally, a short summary will conclude my talk. So let me motivate the audience about the need, right, for real-time ultra-high-speed or ultra-fast imaging. The first reason is that many dynamics are either non-repeatable or difficult to reproduce, right? So if you look at the phase transition, right, from crystallization to amorphous, then once the phase transition is down, right? So it cannot be undown. So that's why if you want to document this event, right, so it has to be done in real time. So biologically, I mean, you can see that for spontaneous neural activity, I mean, well, maybe the pattern is reproducible, but it's very difficult to do, right? And the second reason is that, well, conventional pump and probe based method may have some limited accuracy and efficiency, right? So if you want to use a laser, right, to watch the time evolution of certain parameters that you want to investigate, it's very difficult to keep the laser running at the same intensity, right? So there may be some inaccuracy. And also, usually, right, you can watch the time evolution of the time delay with 1 parameters under investigation. So if you want to, say, record or optimize multiple parameters, sometimes usually takes you a lot of time. So overall, the pump and probe based method is not that efficient. So this is why real-time ultra-high-speed imaging is quite attractive, because in one acquisition, right, you essentially get a movie, right? So it contains 2D in space and 1D in time. So in today's talk, I want to focus on specific optical phenomena that enable us to do ultra-high-speed imaging, that is streaking, right? So what is this one, right? What is streaking? So in this image, so we basically see that there's some light trails, right, leaving by a fast-moving car when you have a photography taken with a long exposure, right? So essentially this is streaking. So we're actually looking at a light trail, right, leaving at different position over the time. So streak can actually help us to get high-speed imaging. So why do I say that? Because if I look at this, I guess, cartoon, right? So it shows the dynamic scene, right? So if we use a, let's say, normal speed camera to capture this dynamic scene, what we will see is essentially like this, right? So the temporal information is actually integrated, right? So you get basically a temporally integrated image, and imaging temporal information are stacked up, and you won't be able to resolve them. But if you somehow can streak it up, right, so basically share it to different spatial position, then you can actually convert time into space, and this allows you to resolve or review the temporal information. So conventionally, streak imaging is done dominantly by a device called a streak camera, right? So this is basically a schematic of the streak camera. So in the conventional setting, everything has to go through this very narrow entrance slit, and then you use a streak tube to deflect it, so that you use a internal CCD camera to capture this streaked image. So one spatial axis is still used to display space, but the other spatial axis now is display time, right? So conventionally, streak camera is considered to be a one-dimensional ultra high speed or ultra fast imaging device. But by combining the concept of compressive sensing, you can also push it to a 2D ultra fast camera, right? So this is done by using a digital micromirror device to encode the dynamic scene. After that, the encoded dynamic scene is relayed to a wide open entrance slit now. So there you have a photocathode where the photons will be converted to photoelectrons. And then you add a time varying voltage to deflect these photoelectrons to different vertical positions according to their time of arrival. After that, this signal is amplified by a MCP or a microchannel plate. After that, the photoelectrons will bombard on the phosphor screen. So there they will convert it back to light again and finally get measured by the internal CCD cameras. Okay, so what I'm showing here is a trillion frames per second compressed ultrafast photography system, which still holds the record of the frame rate in single shot passive imaging at 10 trillion frames per second. But now we're talking about computational imaging. This is only half of the story, because after that you take the image and put it into a computer to do image reconstruction, and this is the movie that you will be able to see. So here we're seeing the beam splitting of a picosecond laser pulse. So everything works, but there's some intrinsic limitations, and everything is posed by the streak camera itself. First of all, we have to use a photocathode. Immediately when you use photocathode, then you realize that there's a trade-off between the quantum yield and temporal resolution. At the same time, because photocathode works by photoelectric effect, it has a very, very low sensitivity when the wavelength goes beyond 900 nanometers. So basically, for infrared imaging, the streak camera does not work, right? Second, the streak camera relies on photoelectric imaging, but if you are doing that, then you're automatically reduce the spatial resolution by the space charge effect. And finally, for the MCP, sure, it can amplify the signal, but it has a limited field factor. So all these things combined made the streak camera a very low efficient device to use. Okay.
Are you allowing only one row of information to go through the slit? What's the role of DMD?
Right. So the role of DMD is to basically add a random encoding mask to the dynamic scene. So it's 2D, right? But I mean, you can think that if you go to a supermarket and get a bowl of milks, right? I mean, so there's some barcodes. So I mean, maybe before you don't know which milk is which, but I mean, once you have the barcode, you can distinguish them. So DMD is actually give you this barcode, right, as a prior, so that you can tag the temporal informations from each frame. So then you don't need to go through a very narrow entrance slit, but you actually open up this slit. So then that means that, well, if you have a 2D image, that's frame number one. But after you go through this sweet electrodes, the second frame actually shared up a little bit, right? So sure, they have overlap. But since you have encoding, it doesn't matter because, I mean, that's your prior. So even if everything is compressed together, you'll be able to use computational method to reconstruct it. So this is how we can actually use the DMD to add another spatial dimension in the measurement to convert the streak camera from a 1D ultrafast imaging device to a 2D snapshot camera.
Yes.
You mean the slit in the streak camera? No, we'll open it up. Yeah. Great question. Actually covers one slide I'm going to talk about. Anyway, so all right then. So let's continue. So we have well, now we know that for optoelectronic streak imaging, there's some limitations, and we want to use the optical method to overcome that. So how should we do this, right? So if we want to use coded optical streaking to record the temporal information, the underlying principle is the same as the optoelectronic counterpart. We still do encoding, and then we streak it, and then we record. But now, since everything is done optically, we have lots more flexibility, right? For encoding, we can do it in the spatial domain or reciprocal domain. And for streaking, the underlying principle is to couple time information with one of the photon tags that you will see in the planoptic function. So usually you have 7, right? So get rid of time, we'll have 6, right? So this is the underlying principle. So we couple time with one of them, and then we share this couple the photon tag onto one of the spatial axes. So this eventually we link the T with one of the spatial axes, let's say X, right? So this is how we streak it out, and then we record. So let's take a look first of how we can do encoding in the reciprocal domain, right? So the underlying principle in this area is we want to break the continuity in time by encoding the spectrum or angles, right? So this is a very famous ultra-high-speed imaging device called STAMP, right? STAMP stands for sequentially timed optical mapping photography. So as you can see, they use a chirped pulse to come in, but they use a spatial light modulator to do encoding after the beam gets Fourier transformed, right? So this is what I mean by reciprocal domain encoding. So after that, it basically breaks this continuity to a multiple isolated pulses. So this pulse train is used to probe the dynamic scene, but as you can see, each pulse actually has a different frequency, right, represented by different colors. So that's why at the detection side, you can just simply use a grating to share this spectral information to different to different spatial locations. So here, I mean, you have noticed that, I mean, from frame to frame, they cannot overlap, right? So this is how they can do framing or mapping photography. So the advantage for encoding in reciprocal domain is that once you have the image, right? So you stack them together, then here we go, right? So you have your movie. There's no need to do image reconstruction. And also, since we don't need to do any sort of encoding in spatial domain, you have a higher spatial resolution compared to the computational counterpart. However, since frame to frame, you cannot overlap in space, you have a limited number of either frame size or sequence steps. So a more popular way to do the encoding is actually in the spatial domain. So to do this right, we have to make sure that each frame in a different time point needs to be encoded by a different or unique mask. So this is usually done by using a random or pseudo-random binary mask. You may wonder, well, I mean, do you change the mask? No, the answer is no, right? Why this one still works, right? But if you analyze the correlation between any two rows or any two columns, you find out that they're essentially independent, right? So even if I use a static mask, the streaking actually allows me to integrate rows or columns from different part of the mask. So that's why each frame can still be regarded as having a unique mask. Second, to do this right, you have to select proper devices to do the streaking, right? So as 2 examples, if you use a rotating mirror and a collimation lens, you can couple time with angle and space. If you use a chirped pulse with a grating, you can couple time with wavelengths and space, right? So these are 2 typical methods that allows you to do all optical streaking. So this is what you will see after you streak it out. So as you can see, well, I mean, I have the coded, right? I mean, I have encoding in every single frame, but I mean, this encoding allows us to use a prior information to mix the time and space. So in this way, if we leverage the sparsity in this domain, we'll be able to actually recover a movie. So compared to the encoding in the reciprocal domain, the encoding in the spatial domain actually can give us a better either the frame size or number of frames in the movie. All right, so after these two sections about fundamental theory, let's talk about how we can implement that in reality, right? So the first work is done by my student Xiang Lei, and we published last year in Optica. So this work is called diffraction-gated real-time ultra-high-speed mapping photography, or with the acronym of DRUM photography. So this is the system schematic. As you can see, we first image a transient scene by using this objective lens to the intermediate image plane. After that, the image actually processed by a folded 4F system. So from here to the DMD, we use a stereoscopic objective lens to do a Fourier transform, and we use a DMD at the Fourier plane to do encoding. So everyone knows that DMD can be considered as a 2D diffraction grating. So this is why if you have a 1 beam input, you can actually generate lots of diffraction orders, right? So 7 of them is going to be lined up in the axis or X prime axis. From DMD back to this direction, we have to go through the stereoscopic objective lens again. So this means that you have to take another Fourier transform. So this is why at this plane, you actually generate 7 replica of this transient scene. So they are relayed to a CMOS camera. So far, everything is, I guess, common when everything is static, right? But now if you synchronize the generation of the transient scene with the inter-pattern transition of the DMD, interesting things will happen, right? So as you can see here, this inter-pattern transition of the DMD is equivalent that you add a time-varying phase profile onto the dynamic scene, right? So this allows the diffraction center to be swept through the 7 diffraction orders sequentially. And this allows us to use the diffraction as a gate to gate out sequential frames from the duplicated scene. And we put them together, and this allows us to have about 5 million frames per second imaging speed. So we can do 7 frames, and each one of them have 200 times 200 pixels. So after we build the system, we characterize its performance, right? The first thing that we look into is spatial resolution. So we put a resolution target there and try to measure the performance. So I mean, we see that all 7 frames, they have a resolution of 3.5 micrometer, which is very close to the NA limited diffraction spatial resolution. And then we moved on to measure the temporal response. So we put a photodiode and to measure the temporal response in each diffraction order. So this allows us to figure out the frame interval is 210 nanosecond, corresponding to a mean frame rate of 4.8 million frames per second. And if we consider the finite field of view in each frame, the temporal resolution is 370 nanosecond. And then we moved on to demonstrate this system in 2 applications. The first one is we imaged the ultra-fast laser-induced plasma generation and cavitation. So we shine a femtosecond laser pulse into cuvette with water, and we shine the 473 nanometer laser beam as a probe. So this is the real-time result when the pump energy is 9 microjoule. So as you can see, we start with the plasma channel, and the plasma channel collapses to a small bubble. Now, if we increase the pump energy to 10, then things will change, right? So the plasma channel is still there, but I mean, and then, you have a larger bubble generated. And we can also do front view observation. Right here, we focus on the bubble expansion, but as you can see, we can see lots of ring structures surrounding this bubble, and we can use the theoretical. We can use the theory to fit this function, which verifies that our experimental result goes very well with the theoretical prediction. And the final experiment is that we did laser ablation. So we focus a 9 microjoule femtosecond pulse onto a single layer onion cell and watch how the sample is damaged. Okay, so this is a real-time movie. So then we can analyze this movie and get some quantitative measurement, right? So we can see that if you analyze the ablated area, it's very interesting, right? So from the first frame to second frame, you see that the damage is instantaneous, and this is due to the like optical ablation. From 0.2 to 1 microsecond, the damaged area goes up very, very slowly. And this is attribute to the fact that we are still within the thermal confinement regime, right? So even though the energy is deposited by the femtosecond laser pulse, the heat is not, propagating out, right? So this means that, there's no much damage generated by the heat. And after that, then the heat starts to diffuse and you see the faster damage. Right. So, we also found out that, the damage is mainly goes in this direction. So I think we don't investigate this in detail, but we believe that the fact lies in how the sample is oriented, and there also be some heterogeneous structures in the sample. Okay. So drum is actually a image modality that we induce optical streak imaging or coded optical streak imaging with encoding in the reciprocal domain. But how about in encoding in the spatial domain? I would like to show you two examples. The first one is a paper that we published in Nature Com back in 2021, and this one's called SPLIT. Okay, so single shot photoluminescence lifetime imaging thermometry. So the imaging system actually contains a three-part. So we use a 980 continuous wave laser with a chopper to generate 30 microsecond pulses. And these pulses will be focused at back aperture of the objective lens, which will give us a wide field illumination to induce the photoluminescence intensity decay from the rare earth doped nanoparticles. So here we use the sodium gadolinium tetrafluoride as upconverting nanoparticles to indicate the temperature. So these nanoparticles, they will sequentially absorb 2 or more near-infrared photons, and then they will emit in the visible domain. So we're targeting 2 bands, right? So either the green band or red band. We use a filter to select the band we want to image. And then we put a beam splitter to generate 2 channels, okay? The first channel is basically directly shine into a CCD camera. So there you have a temporally integrated image, right? So the second one is actually processed by a coded optical streaking system where we use a high resolution printing to generate a mask, and we use a gavel and a lens to do streaking. So after that, we send these 2 images into a computer where we use a PNP-ADMM to solve a minimization problem. But of course, you can use machine learning to do the image reconstruction. The output from this computer is really a movie, right? So we have 100 frames. Each one has 460 times 460 pixels with imaging speed of 33,000 frames per second. So it can be tuned, but here we select the 33,000 to get the best signal to noise ratio in the luminescence decay function that dynamics that we're trying to measure. And finally, because the photoluminescence lifetime of rare earth doped nanoparticles is related to the temperature, we can use this equation to map the 2D temperature distribution. So the first demonstration that we did is we put nanoparticles, cover that with some transparencies, and then change the temperature from 20 all the way to 46 degrees. So here is the real-time movie showing the photoluminescence decay. So if we do color-coded, then we can actually see that when the temperature goes up, for both red and green emission, their lifetime goes down. So this allows us to establish the lookup table that links the temperature and the lifetime. So this allows us to, that allows us to use it as a criteria for the ensuing experiment. So we put nanoparticles under a chicken tissue phantom to the phantom experiment, and then we cycled these phantom. We cycled the temperature of these phantoms from 20 to 46 degrees for about 4.5 hours. So as you can see, the measured temperature actually goes very well with a preset one. And finally, to demonstrate this system in a biological environment, we demonstrate the video rate temperature mapping of a biological sample. So we load the nanoparticles into a single layer onion cell, and then we move the sample underneath a microscope at about 1.2 millimeter per second. And we use a split system to do a lifetime temperature mapping at 20 frames per second. So here goes the movie, right? So each frame is a lifetime based lifetime map that can also convert to be temperature. So to show some quantitative measurement, we actually selected 4 regions. So as you can see, these 4 regions, they have different intensities, right? But the photoluminescence decay, they're pretty much the same. So this actually shows that photoluminescence lifetime can give you a more reliable measurement compared to the intensity counterpart. And also we traced these 4 regions, right, when they moved across the field of view. So once again, I mean, you can see that they have different trends, right? So the yellow region, the intensity goes down, the magenta region goes up, and the blue and cyan region or green, they stay pretty much the same. So once again, if you use the intensity-based method to do the temperature analysis, you may have lead to some very confusing and inconsistent result. But immediately when you switch to lifetime, you see that, yeah, they all pretty much stayed in constant line, which indicates that temperature doesn't change, which is the case for our measurement, right? So right now we're using the split to explore different applications. Yiming actually lead this project with a collaboration of 2 professors from University of Montreal, where we use lifetime to indicate the temperature and use temperature as a biomarker to see micromelanomas. Okay, so we load the upconverted nanoparticles into a micro needle array so that we can inject to mice painlessly. And then we did a thermal stimulation. So we cool down the temperature to be about 15 degrees and watch the thermal recovery. And we found out that if there's a lesion, the recovery rate is faster and the equilibrium temperature is also higher. So previously, I mean, people try to use a thermography to do the cancer detection, but their minimum detectable size is 15 millimeter. So if you talk to a dermatologist, they will say like, okay, it's clinically irrelevant because in ABCDE rule, D has 6 millimeter. So with our research, we have shown that, yeah, I mean, if you look at this one, the tumor size is 2 to 3 millimeter. So we think that we have a better technique that will break the conventional criteria. And we're also exploring different spectrum, right? Because we're doing all things all optically. Then in principle, our technique should work with any CCD or CMOS cameras, right? So in this paper just published in Advanced Science, Miao actually switched the camera from EMCCD to InGas, right? So there we are using that to do a anti-counterfeiting. So this is a flower sample, right, as a target. If you use the intensity to see that, you basically see, there's not much signature. But if you switch to a lifetime, then you see that we actually add a different sort of nanoparticles in one of the petals. So this signature can only be shown up when we use a temperature, when we use a lifetime to do the measurement. Of course, we can do 2 petals and we can make it as complicated as possible. So that, once again, showing that lifetime-based measurement can give us additional additional information that help us to enhance the information security. Okay, so yeah, so we can carry this, right, to couple time and wavelengths and space. So in this work, Jinyang and Miguel, they actually combined a chirped pulse to literally what David has developed, I guess, 20 years ago, is basically a dual sharing cassis system so that we can actually see things very, very fast, right? So we call it swept coded-aperture real-time photography, short for SCARF. Then in these 3 movies, you can see that we are actually seeing the how a chirped laser pulse transmits through the different transparencies. And also we did a experiment to showcase its interaction, or showcase the interaction between a shaped femtosecond laser pulse to semiconductor. So there we bring in a pulse, pumped pulse, and we let it go through a cylindrical lens. So you generate a line, right, in a zinc selenide plate. And by tuning the angle, you can actually think that different part of the pulse will arrive at the sample at different time point, where if you link everything together, essentially you will see a propagating absorption front. So we use this probe pulse to probe this and use a SCARF system to actually see this propagation pulse front. And if we put the time and the distance together, we can see that this propagation speed is 8.7 times 10 to the 9th meters per second. So yeah, we're very fortunate. This paper was just accepted yesterday. Now, Miguel is carrying this work even further. So we're exploring medallions. So everyone knows that the medallions can be super dispersive. So now if we use a chirped pulse to convert or to map time with spectrum, then we can actually use the medallions to do both streaking and imaging, right? So this will make the system very compact. So we also designed a new neural network that uses a deep unfolding net to embody the forward model that we're using for this hardware system, and we use UNet to improve the result. So we only have the simulation result, but I mean here you can see that we're simulating a propagating terahertz cone, or you can call it a Cherenkov radiation at terahertz. So we can actually see the details in a very accurate manner. So now let me move to the last one. So I mean the coded optical streaking can also help us to do single pixel imaging, right? So what is a single pixel imaging? Well, basically they want to see 2D image, but they only want to use a 0D detector, right? So obviously there's a mismatch in dimensionality. So how to solve that? So for single pixel imaging, they're using 2D encoded patterns to modulate the scene and then integrate everything. So they change the pattern, you have lots of bucket signals. And then once that's done, then you basically do the inversion, right? To recover the scene that you want to see. Single pixel imaging can work both actively and passively. And compared to the 2D image sensor, right? I mean, it has some advantages in sensitivity. I mean, they are more reliable, more available in the non-visible spectrum, and also it has a better cost. So for single pixel imaging, it has lots of problems, right? So perhaps the biggest one is speed, right? Because even if you look at the DMD, which is considered to be the fastest spatial light modulator, it has what? I mean, 22 or 32 kilohertz projection rate. So people try to use compressive sensing to reduce the number of projection, but still, I mean, you won't be able to gain much, right? You gain a factor of 2, a factor of 3. So then people think about, okay, what if I use, basically light patterns that can flash very, very fast? Well, sure, it works, right? But it cannot allow the system to work passively, which actually eliminates the aspect of the photography, right, for the single pixel imaging. So people also think about to do things passively. So they try to fabricate a pre-designed mask and spin it very, very fast. But once the pattern is done, right? So this actually means that the system is not reconfigurable. So our motivation is that can coded optical streaking allow us to do ultra high speed, reconfigurable, and real-time single pixel imaging. Well, the answer is yes, right? So we published this paper in Nature Comm in 2022, and this is Patrick's work. And this system is called Single Pixel Imaging Accelerated by Swept Aggregate Pattern, acronym SPI or SAP. So essentially, we use a DMD with a dual passing laser scanning to speed up the pattern projection rate. So as you can see, we shine a laser beam and we use this lens to focus that in the moving polygonal mirror. And then it's collimated and routed to the DMD. Now, if the polygonal mirror is moving, right, it's rotating, then you can actually see that the beam that goes to the DMD swept through the entire DMD surface. So that means at each time point, we're actually seeing a different part of the big mask that I load on the DMD. So if I use a correct mask, we'll be able to leverage some very interesting mathematics to do the reconstruction, which if I have time, I'll be happy to share more details. But what this design is special about is that after the encoding, we bring the beam back to the moving polygonal mirror. So this dual scanning actually cancels the sweeping phenomena, so that at the output plane, you actually have a stable field of view, but the pattern is actually sweeping, right? So this is how this is the animation to show how it works, and this is basically a pattern on the very famous bunny object to show the flowing, right, of this pattern. So mathematically, we can actually squeeze n patterns into one DMD pattern that we loaded. So equivalently speaking, we can improve the pattern projection rate by n times. At the same time, we still use a DMD, right? So that's why the SPISAP system retains the reconfigurable advantage that has been shown up in most of the DMD-based systems. So in this example, we demonstrate imaging speed from 103 all the way to 12,000 frames per second with a frame size of 11 times 13 pixels to 101 times 103 pixels. So here are some examples. So first, we imaged the burnout of a light bulb at 300 frames per second. So you can see smokes, you can see fires, and also you can see a segment of the filament actually burned down, right? And then we can push the imaging speed to 12,000 frames per second. And these are 5 field of views of a fast rotating chopper. And finally, we can do real-time SPI. So this is what Patrick is showing is a real-time demonstration of a mechanical watch, right, imaged by a single pixel imaging. So real-time SPI is rather rare, and because we can project the pattern very fast, receive very fast, process it very fast, combining everything together, we have a SPI. So I know that David has an opinion, a certain reservation about single pixel imaging. So let me show you something that I don't think the current 2D camera can do. Okay, so not very long ago, we actually demonstrate this SPI-ASAP with a far wave, right, infrared spectrum, right? So here the application is we want to image the temperature of the inner canine of a human being, because I mean that's the only place that you essentially have meat, right, exposed. So you don't have the skin to cover that. So the temperature in these areas actually reflect more accurately your core body temperature. So we're actually using this one to show that, well, I mean, even we use a single pixel camera, we'll be able to screen the temperature. So we're prepared for large or massive screening, no matter if it's for COVID-19 or any other influenza that may or may not come, right? So we also did this at different time point during the day, and we found out that, yeah, I mean, the human temperature actually has a cycle, right, in the period of 6 hours. So this actually goes very well with some existing literature. Okay, let me summarize. We talk about the coded optical streaking today, right? So the key aspect is that we want to leverage the photon tags in the planoptic function to cover time with some of the intermediate photon tags. And these intermediate photon tags will be coupled with space when you do streaking. So eventually we can couple T with X to do streaking, right? So because we can do that in optically, we don't have to go through photons to photoelectrons back to photons, as they usually do in the streak camera. So that means all the limitations imposed by the streak camera doesn't exist here, right? So this gives us lots of flexibility. So I just showed you 2 typical designs. Either we encode in the spatial domain, or we can encode in the reciprocal domain. So in the spatial domain, we're in the computational high-speed imaging part. If we encode in the reciprocal domain, this will give you an ultra-high-speed mapping of framing photographies. So each has, advantages and disadvantages. So it really depends on your applications. But no matter what you do, coded optical streaking is an approach that allows you to do 2D ultra-fast or ultra-high-speed imaging in real time. So a key aspect in the coded optical streaking is that you have to use correct optical amounts to realize the sharing unit, or to realize the sharing. So we talk about 4 today, right? So either you can use a fast micromirror flipping of a DMD, or you can use a galvanometer, right, to couple angle with the space, or you can do a dispersion of a chirped pulse, or you can make it a little bit fancier, right? So you can do a dual pass of a polygonal mirror. So more details will be covered by this book that I'm edited. So it will be on the market by April 2024. So finally, as just a few sentences about the prospect, I think we're in the era of computational imaging, right? So when we talk about computational imaging, automatically there are two aspects. So you need to have a better software, you need to have better hardware. So in my opinion, for the software, there are several things that might be very interesting, right? So how can we actually do a real-time reconstruction, right? And how can we use the software to better incorporate the model that we implement in the hardware so that the reconstructed result has a better quality. And finally, can the software really act as a head, right, to control the hardware and to give us this multifaceted supervision to provide the real-time feedback? I think those are some interesting aspects. For the hardware, I think hardware determines the spatial temporal resolution, right? Because software cannot create the data for you. So how well the system will perform ultimately is determined by the hardware. So I also think that multifunctional devices, for example, MetaLens, will allow us to make the system compact, right? And also low cost. I think lower cost is also an interesting aspect to enhance the practicality of the system. So after that, let me acknowledge my team as well as the funding support from federal and provincial government. Last but not least, we're recruiting. So we have positions in for graduate student and postdocs. So if you really want to experience the North, right? So the real North. So please come and talk to me. I mean, we have lots of, in my opinion, lots of exciting projects that we hope will recruit the good students. Okay, so I can stop here. This concludes my presentation and be happy to take questions.
So thanks, Jinyang. It was fantastic. Questions for the
Yes.
Trying to get the big picture here. So you have a camera that has a certain frame rate, right?
Yes.
What's the frame rate typically for a good camera?
Right. That's actually a great question because let's see if I can go back. Yeah. So I mean, it's more like a comment, right? So anyway, what I want to say is the operation of coded optical streaking does not disrupt the normal operation of camera. So if your camera running at 20 hertz, let it be, okay? So the key concept is that we squeeze all the temporal information in the exposure of a single frame. And then we use computer to extract the temporal information. So that's why the camera can just shoot at, let's say, whatever the intrinsic frame rate can be. But I mean, in each acquisition, we can actually compress, let's say, 100 frames. And then in this way, we can actually generate or improve the imaging speed by 100 times, 1,000 times. So I mean, the camera can just run it at its normal imaging speed.
Per second.
Yeah, you can. Yeah.
And you're taking your object that is changing faster than that.
Right.
And encoding it with the DMD at a faster rate than the rate of the camera. Like say 10 times faster than the camera frame rate.
That's not 100% accurate because I mean for DMD encoding, right? So let's say we're talking about the femtosecond event. The DMD, right, can run at 32,000 hertz. So the pattern changing rate is too slow. So that means during the data acquisition, the DMD pattern actually doesn't change. So it's a static encoding. So how to make this pattern different is actually through sharing, right? So imagine that this is the DMD codes, right? So we actually encode the entire data cube, right, with the same pattern. But if you look at two adjacent frames after the sharing, they actually, will be shared by 1 pixel, right? So in this way. So that means if you analyze, for example, the first row of the second image and the second row of the first image, they can be considered as linearly independent. So in this way, we can regard this shared same encoding mask as two individual unique masks. So this is how we can actually retain the temporal information through the static encoding. Yeah.
Or encoded frames are not presented to the camera, and you get one frame
Right.
out of those multiple
So
objects.
exactly. Yeah.
And then you go back and reconstruct the
Yes.
frames, the actual sequence of frames.
Yes. Yes.
Kevin, what about these students? On your slide 13, you showed a really nice kind of summary slide. By the way, this is really exciting work.
15?
Oh, 13.
13. 13.
Yeah, so a lot of interesting stuff. Thinking about this, it's the CT problem. I know classically when we think about CT, we need to oversample or do high density sampling.
Yeah.
And then we have to deal with non-uniform sampling in the center. With your system, I think you're making the big distinction that the DMD is used to help you disentangle space and time.
I think about it now, yes.
Yeah, and because you still have practically overlap, your algorithm has to figure out how to just do that disentanglement.
Right.
And because just like if you don't properly filter in CT, you get a space-time kind of blurry, low-frequency signal in your reconstruction. Alternatively to DMD, I was wondering if you did it optically without an electronic changing system. Instead, you make it clear you have the aperture completely open. But normally, we make the assumption space and time are independent of each other.
Right.
But in reality, the only signal you're interested in is if the object moves in space.
Okay.
And so by using multiple apertures at slightly different focal planes, just adjacent to each other, then you can have each camera focusing on a different slice in space. And so you can directly disentangle the temporal information because each aperture is focused on a different thing. And so you directly optically have independently separated space and time.
Wow. Okay. I think this is a good idea. I actually didn't think about in this direction, but first, let's get the concept clear. Okay. So most of the stuff that I'm talking about today, we're doing 2D ultrafast imaging, right? So that means, yeah. So now if you want to have a camera array, each one of them will focus at a different, I guess, depth direction. Probably will work like what you said if the object is moving towards you, right? Or in the other way, right? Yeah. Right.
Yeah.
Yeah, but I mean, how to do this when you have something that moves around in the same, let's say, 2D plane? That's something that I don't have the answer for you right now. So for us, we also work in tomographic imaging, but we actually do this not through single shot, but multiple shot. So we're actually thinking, I don't know if I have a slide, but anyway, so you can imagine that, I mean, for this one, we're looking at X, Y, and T, right, problem, and we're doing streaking. So that means depending on the power of your streaking, you can do it, very gently, or can do it, like with extreme. So now if you put it back together, actually this equivalent to say that you're actually looking at the XYT data cube from different angles, right? So we have a technique called QD. So it's like compressed ultrafast tomographic imaging, where we actually just change, for example, the Gavos Gavos speed, so that we can have multiple measurements. Each one of them is actually looking at the sample at different angles. So then we used the sparse view CT reconstruction algorithm to retrieve the XYT information. So that can be done. Exactly, yeah. So the advantage for that one is we don't need to do encoding. But the downside is we have to do it in multi-shot. So we're trying to think to use the chirped pulse with grating to do this in a single shot. But I think there's a way. So I hope that answers your question. But I mean, to your proposed whether or not this can be done, I have to think a little bit more, right? So I think there's a way, but I mean, maybe works only for specific types of transient event. That's how I.
moves along X, Y.
Hmm.
Oh, yeah, sorry. Yeah.
So I have a comment and a question.
Okay.
So first, the comment, I think, was like very nice to see, the parallel to hyperspectral imaging, especially David's work. I think it was like very nice. So how you explain that. And now the question. So you like very nicely explained streaking, where you basically streak out time in X, right? Is it a useful idea to also streak out to different dimensions, or possibly also to different modalities like polarization or something like that? Is that a useful thought, or is this stupid?
Oh, no, this is not stupid at all, right? I mean, so obviously, so I think a general trend is like, okay, you have, let's say 7 or 9 photon tags that you can work, right? So the ultimate goal is, okay, you want to link T with something, right? So as long as this something can be measured at different, or let me put it in this way, as long as some photon tags can be resolved in this measurement, then I think you have your streak, right? But I mean, most of us will have, a 2D camera, right? So camera links to space. So that means ultimately, I think T and X, they're fixed. So, I mean, how to link them? You can directly link them, right? So some people use a pulse from tilt and to measure the terahertz pulse, or right to do the to measure the electronic pulse profile. I mean, that's a direct link. Or I mean, you can use a theta, or you can use a lambda, right? If you want to use a polarization, yeah, sure. But I mean, the polarization has to be changed over time, and maybe needs to be done continuously, right? Yeah, so maybe there's you can use a crystal and try to add a voltage, right, to do this. But eventually, it has to be reflected in the spatial domain. So I mean, how to measure this rotating polarization using I mean, in space? Probably you can use these polarization encoded cameras, right? So yeah, so.
Thesis on spectrospatial polarization. They did it.
Okay.
Paper.
Yeah, me too. Yeah.
So very inspiring talk, especially this dispersive, concept. I'm wondering, in all of this is active pulse, engineering and then receiving of that.
Right.
Have you thought of a counterpart of this for a passive system where you don't get to choose the illumination temporal? Maybe you can shape the spectral, dimension, but it's not pulsed or controllable.
Right. I mean, yeah, that's a great idea. We thought about it, but I mean, here the concept has to be you first chirp it, right, and then you probe it. So instead of doing, like a T and omega Fourier transform, you actually do mapping, right? So T1 is mapped to lambda 1, Tn is mapped to lambda n. So if I want to do it passively, the emission from the dynamic scene, its color spectrum has to be different at different times. So we haven't found a ultrafast event that has this optical characteristics. So that means, I mean, if imagine that is basically just white light coming towards me, then yeah, I mean, I have basically the spectrum, encoded spectrum that's at everywhere, right? So when I put them together, I mean, I won't be able to get it back. So I think the coupling between T and lambda has to be there. So no matter if I do it actively or I do it passively, I think this will kind of like serve as the foundation for me to do the extraction. So.
Right. So if you're doing ranging, passive ranging, can use some property of light. I'm thinking explicitly of coherence, spatial or temporal coherence, which you don't explicitly control, but you can exploit.
I see.
Do something like this. Anyway, we can chat about that.
I think probably. So I mean, if I understand you correctly, it's more or less like a OCT type of thing, right? So I mean, you use a coherent gating to extract the I guess the interferogram and try to extract this one. So yeah, so for that, you still probably need to measure it very fast. So I think you probably don't need to use the spectrum as the photon tag, right? So you just need to have a camera that measure as fast as possible, so that you can actually resolve this interference, right, on the spatial axis. But yeah, so I mean, when I was a postdoc, we actually used the cup plus a picosecond laser pulse to do LiDAR. So yeah, it's a scanless because we can see the time of flight. So that can be done. So if I want to explore the kind of like quasi coherence gating, I think the device may be a bit more complicated, but I mean, I think in principle it should be okay.
Yeah, really awesome. We were exploring a little bit of high-speed imaging in our lab, and I was curious because you mentioned the Fourier space as well. Even like if we take a toy example, like a circle, just a plain background, it shifts in 2D. The Fourier space should be the same, the real part, but the imaginary part of that, when you compare this, will have that shift there,
right?
That phase offset.
Yeah.
Are you guys doing analysis of that space? Where you?
Not really. Yeah. I think this links to what David was talking about in photonics West, right? So it's a little bit, but no, we're not doing that. So far, everything is intensity based, right? So we thought about how to do that. How to say? I mean, to analyze a complex light. So I think right now, I mean, if you're talking about the phase measurement, I think for us, probably the easiest way is to split the beam to one is with focus, the other one is slightly out of focus. So we can use a TIC to transport intensity equation, this type of stuff to retrieve the phase. Yeah.
When you do the Fourier transform from the image, the phase itself, that imaginary phase, the imaginary one will have this.
Yeah, I understand that. Yeah, but I mean, somehow we haven't think about the way to leverage this aspect. Yeah, but I mean, yeah, I mean, if you have some ideas, I'd be more than happy to talk. Yeah.
I mean, the reason that this method works is that the spatial Fourier spectrum of the object is much smaller than the extent of the spatial frequencies that the camera can capture.
Mm-hmm.
So that's why you can separate individual frames in time. How close is your method to the theoretical limit? Because the theoretical limit has to do with the ratio of the Fourier spectrum, spatial Fourier spectrum bandwidths of the camera relative to the object.
Right. That's actually a great question, right? So, I mean, first of all, I don't have a specific answer to your question, like how close we are. But I mean, the thing is, like, immediately when we use a code, right? I mean, to do encoding, we actually limit ourselves, right? Because if you're talking about the camera pixels, usually we need to have a 2x2 camera pixels per encoding pixel. So that automatically actually restrict us in the spatial frequency domain. So if we want to push it to all the way to the limit, we haven't actually do this either experimentally or with simulation. So how close we are. But I think you are right that I mean, for the information that we can contain, I mean, it has to have a limit. So we actually sacrifice part of the spatial bandwidth in order to gain the ability to recover the time. So in practice, what we do is we sacrifice, for example, if we want to do it with do this with a microscopy, we'll probably magnify the image a little bit bigger, right? So we sacrifice the field of view, but we make sure that after we do encoding, do the reconstruction, we can still have a resolution close to the NA limited space. But I mean, yeah, I agree with you that we sacrifice this to gain the temporal.
Just for a minute, just because I won't. I should put it as a question somehow, but this is it's not frequency domain multiplexing. It's code domain multiplexing. So the channel is underutilized. In an imaging system, the channel is underutilized. You don't give up information in a compressive system. You utilize the channel more effectively. And so it's a core question, but it's not trading frequencies for resolution, it's doing code division multiple access. So it's a spread spectrum technique. And you're limited by the channel capacity, but you haven't given up anything necessarily because your image was no imaging system naturally uses the full capacity of the channel.
But in reality, right? I mean, you cannot do, let's say, one encoding pixel to match with one camera pixel, right? Usually in this case, you always have to do a, satisfy Nyquist, right? So right.
A point target coding cannot allow you to superresolve a point target.
I agree.
But images don't consist of point targets. Images consist of features.
Yeah.
And you don't necessarily you reconstruct those features by using the spread spectrum technique.
Okay. But to me, I think in practice, I think there's still a limit imposed by the encoding mask. So after that, I mean, because your mask is definitely going to be bigger than the camera pixel size. So
I would say the encoding allows you to get much closer to the so you're limited by space bandwidth product for the overall capacity of the channel.
Yeah.
But the imaging systems never get anywhere close to full capacity of the channel. Right? The encoding mask allows you to use the channel much more efficiently. You're getting more information through the channel than you would get if you didn't do the encoding.
Okay. Well, we'll have to talk about this, I guess. But anyway, yeah. All right. Very good.